Our next presentation is designing a productized building system. And our presenter today is Sara Pacelko. She's the director. I apologize my accent if I just... She's the director of product design from Volumetric Building Companies. So there is a summary about our presentation. I'm going to just read the first phrase because I don't want to steal it from you. But I want to talk a little bit about you before you start. So this presentation will review an approach to developing a volumetric modular building system that aligns to business and manufacturing strategies. And then she's going to tell us more about it. But Sara, she leads a global team of inventive, passionate, and driven professionals who work together to develop full building systems for industrialized construction. Her team utilizes design thinking to develop new products with a heavy focus on design for manufacturing and assembly, DFMA. So again, just a reminder, questions on Post-its, and we'll be passing around to capture those. Thank you. We are delighted to have you here.
Thank you, everybody. I'm very excited to be here today. This is my favorite topic to talk about, and I'm so glad I get to share with you today. Trying the technology. There we go. So we're going to be focusing on 3 steps. The first is setting objectives. This is a very, very important step, and this is how we set the stage for our product. We have to understand what our product is trying to achieve from a business perspective and a manufacturing perspective, as well as shareholders. And within that is iteration planning. So we don't start with everything on day one. We build into that in the future. The next is development. Here we'll be talking about design thinking on different methods of taking something that's big and massive and a little bit scary, which is a huge building system, and breaking it down into parts that can be pushed through a design thinking method. The last one is zooming into DFMA, so design for manufacturing and assembly, so we can focus on that one stakeholder and that one process and work through it together. Setting objectives. All right. So the 3 big ones that we are going to talk about are business objectives. This has to do with the company's goals for design flexibility, market reach, and manufacturing efficiencies. We can't say yes to everything if we want something that's not a customizable product, for example. Coming out of that will be our market. Is our market going to be accessory dwelling units? Is it multifamily? Is it hotels? Geographic areas, are we focusing in on one specific area, or are we having a global outreach? Next is our manufacturing objectives. So are we investing in high capital costs for high automation, or are we keeping a very flexible and more low-cost manufacturing environment? And lastly, our stakeholder objectives. We are all stakeholders in the process in this room. We have a voice in what a product means to us, and the way that we uncover that as product designers is by utilizing user stories. Out of that comes our outcomes, which inform our assembly strategies. It informs our features, which are connected to user benefits, etc. This is my second favorite diagram in this presentation. When we get to my first favorite, I will let you know. This one, the reason I like it so much is that it starts to break down a bias that I hear in the industry, which is that manufacturing or volumetric modular is either completely flexible, it can be anything and do everything, and it's just prefab in a factory, or it's really restrictive. It's a select variant model. And the fact is that there's a lot of options in between those two. When we look at this top one, engineer to order, we're all pretty familiar with engineer to order. This is conventional construction and prefabrication. We don't start from scratch when we start designing a building, period. We have codes, we have pre-engineered 2x4s, we've got wide flange beams. We know what those values are, and we're not starting with reinventing that. We have that in our back pocket. That's part of our just product platform in building design. The red zone in this diagram, that is our product platform. The blue zone in this diagram is our project delivery stream. So the more we build in our product platform, the less needs to be figured out in project delivery. So we're offsetting responsibilities in a way. So you can see at the top bar, we've got our customer order point, which is at that diagonal. And that is where the customer comes in and says, okay, I want a building, I want a project, let's design it. And then the blue zone is that project delivery stream, as I mentioned. The next one down is modified to order. Modified to order, something to note in this is that none of these are good, bad, right, or wrong. They are just examples, and they match up with different processes. The main thing I want to take away from this is to match up your product with your process, which will be on the next slide. So when we're looking at modified to order, this is something that is used in volumetric buildings, but I've worked with architecture firms that are also kind of modified to order because we've got our standard wall types. We have our standard bathroom types. We know the UL listings that we want to reference in our buildings. We know how things come together. We're not starting from scratch. We have our business standards now. And that is what the generic product structures are in our product platform. The next one is configure to order. This one is really interesting to me. We're now looking at kits and components that work together, and we're building in strong relationships between items. This one, we start to tip the scales between what's in a manufacturing or product platform and what's in the project delivery stream. The last one is select variant to order. This one is pretty straightforward. You have 3 options, you have 3 color options, and you have these apartments and these sizes. Pick your favorite, and then that's what you move forward with. That has the biggest amount of what's in your product platform, but as you can still see by this, the bracket on the right, it has the least amount of design flexibility. So when you increase your product platform, you're getting more certainty and more information, but you're reducing flexibility versus when you're at the top of the chart. Product and process. Okay, this is where we get to start to match them up with process. So engineer to order is a project process and a one-of-a-kind product. So when we are looking at an engineer to order building, we're seeing it on a construction site. That is a project process. The next one is modify to order. Very low volume in the sense of manufacturing volume, so keep in mind that this could have a lot of output a day. So modify to order is connected to job shop. That's a really flexible shop. There's still a lot of variety and flexibility in modify to order, so it belongs in a shop that can have that flexibility in it as well. Configure to order lines up with batch processing, because now we have more certainty, and now we're starting to get into things that can integrate better with machines. Machines like certainty, they like data, they like to have a product platform. And then lastly, we have select variant to order, and that can start being integrated into an assembly line or flow shop because you don't need to have your customer order to know what you're building because you're always doing the same thing. And then the last one is off the charts. We'll never get into it. It's not for industrialized construction. It's more so for commodity stuff, so like oil refining and sugar and things like that. That would be continuous flow. The reason that we want to match things up is if we have an engineer to order product in an assembly line or flow shop, you're getting your low utilization with high capital cost. You invested a lot of money into a factory that can automate and have a high output, but your product doesn't really allow you to have that high output. On the flip side, if you have a select variant to order product and you're putting that in a job shop, you're losing opportunity costs because now your shop can't keep up with product. We're going to focus on CTO in this presentation. Let's talk about market trade-offs. When we are looking at a project, process, or engineer-to-order product, we have some trade-offs in that. The benefit is that we have a large market. We can do anything. We can design anything. We have a massive market to pull from. However, it is, and that's not really a however, it is like conventional construction / prefab. You do get a lot of design freedom, but you get low efficiency and control in that process, especially in manufacturing. When we move the slider over and we start to align more with batch or even assembly line or flow shop towards the other side of the spectrum, we now have a small market. We need to understand what market we're going for in order to design a product to answer that need. We can't say yes to everything, especially on day one, as much as our executives want us to. So we have a small market, but we do have automated manufacturing. However, we have more of a limited design, but we do have high efficiency and control. So these are the kinds of trade-offs to balance when understanding your business objectives. Do you want a big market? Do you want a small market? Are you being really focused to senior living? Or you want to do senior living, hospitality, apartments, and ADUs? Then your product needs to be very, very flexible, which means your process has to be flexible to answer the need. Now we understand our business objectives. We're starting to understand our manufacturing objectives because we understand the process that we're committing to. Those feed into our market trade-offs, which I just described, and that tells us our market size, if we're going to be local or global, and also what our speed to market's going to be. If we really want to get to market fast, that's a factor in how we approach our product design. This leads us to defining our minimum viable product. That's step one. And this is exciting. So now we're going to have our minimum viable product defined. And this is what the company wants to launch in the market to prove profitability. So we're saying, okay, we've made all these decisions. Are they actually going to work? Are they going to be accepted by the market? And we have to be specific with this. Here's my statement that I've already said a few times. Don't say yes to everything in the minimum viable product, because then you'll never be done with your minimum viable product and you'll never go to market. So let's use an example of what that is. So because we're focusing a bit on wood timber volumetric, we're going to say 2 to 5 levels above podium for affordable multifamily housing in Northern California. That's an example of a minimum viable product. We did it. Okay, let's move on. So the first step is defining that MVP, and then we launch it in the market. This is a very traditional product curve in the market. If you've taken a product design class, you've seen this curve before. I've just added MVP for introduction, and then the next stage is iteration 1 for growth. When we launch the minimum viable product, we're going to learn a whole lot about how it interacts with not only the market, but our stakeholders internal to the process. That continuous improvement gets fed into iteration 1. And the goal is that before maturity and decline, we've already started working on iteration 2, and then in the future, iteration 3. So we're anticipating the fact that nothing is fixed, that we do have to change and absorb changes in the market, especially if we're going for a small market. We're going to achieve most of that market by a certain amount of time, and we'll need to have our next offering out before that decline happens. This is a pretty basic iteration planning document example. The minimum viable product is our first step as a company. It can be seen as a test market, and it's typically a smaller scale release. And once it's proved to be successful, by your set metrics, you can define what success looks like to the minimum viable product. Then you start to go into iteration 1. So the red diagram or diamond is indicating when it's released to the project stream. So product design is doing their work, developing the product, it's ready to go, we release it to the project delivery stream. That's when it's released to like architects and engineers to take it and put it into the design of a building, and then it goes through permitting, it goes through shop drawings and into manufacturing, and then finally into set and final assembly, which is construction. So that's what the project stream is. Once it's released into that project stream and we're like, oh, this is successful, great. Or hey, it's successful except XYZ. XYZ goes into iteration 1. And this is where we start to ramp up for growth. We've said to our investors, hey, we have been proven to be successful. We're ready to really ramp up. Let's do this. And iteration 1 takes it and skyrockets the growth, ideally, if you're successful. Iteration planning is a really good way to set aside opportunities that you want to get to in the future that you just don't have time to get to in the MVP as well. So it's kind of a good way to negotiate too when you're doing product design, like, yes, that's a great idea for iteration 1. This is an example of our stakeholders. A really important distinction with product design for construction is that we have so many stakeholders in our process. It's a very wide value stream. We aren't just working with a manufacturer and then the product gets into your hand. It's through the use of, or through the teamwork of our owners and developers, our architects and engineers, manufacturing and production documentation, that's shop drawings, project management and logistics, procurement and supply chain, and construction/final assembly. I like to use the word final assembly for construction because it's part of DFMA. Final assembly is very important to the success of your product. I'm realizing I'm missing one of the stakeholders, which is facilities. And let's walk through a really simple user story right now, which is what our stakeholders tell us. So for facilities, for example, a user story statement might be, the baseline is, as a blank, I want blank to achieve blank. So for facilities, it would be, as a facilities person, I want equipment to be easy to access so I can maintain operations of my facility. So that would be a way to use your stakeholder to create a user story to feed into your product development. This is borrowing from quality function deployment, which is a lean design methodology. So now that we have our stakeholders, we have our objectives, we can start to set what those objectives are with quantifiable metrics. So speed, weight reduction, material savings, cost savings, what are those objectives? And then rank those objectives. We're going to have competing objectives throughout our design process, our product design process. Which one is the most important to your company or to your process? Is speed to market the most important and set aside cost? Or is cost the most important? For our example, minimum viable product of affordable housing, 2 to 5 stories over podium, I'm going to say that cost savings is going to be the most important metric, and that would be 1 and speed second, potentially. These benefits turn into our features in product development. Our users, our clients who are looking at our products, wanting to purchase our products, and in this case, the product is an actual volumetric module apartment, they're looking for the benefits of that system, not the features of that system. So we have to keep those features top of mind and weigh their importance from our end users and stakeholders. All right, the fun part. Now we're going to be talking through what to do next. So we have our objectives. We know what we're trying to achieve, what our goals are. How do we do it? How do we turn these objectives into an actual building system that can be manufactured in a factory? Where do you even begin? This is where I like to begin. I've worked on 4 or 5 different building systems, and this is, in my experience, the best way to kind of cut it up into chunks or bits and pieces to understand a whole building into something that can be figured out piece by piece. We start with defining objects in the system. Very simple. So the object is a part of a building system that can be built independently of other parts. I have a very cheesy Lego model. I wouldn't be a modular architect if I didn't love Legos, so 1 second. So this is an object. It is our ceiling panel. This is an example object. This object has interface relationships with other objects. An interface is simply a relationship. So it's how this piece connects to the wall, for example. There are 2 scales to our objects and interfaces. One scale in a volumetric system, this can be different depending on your system, is the volumetric module scale. This is the scale that happens in the factory. Then there's the scale that happens on the site. That's our building scale. A building is comprised of many objects and interfaces in the site assembly environment. Both of these scales have assembly in them. Objects in our volumetric module scale might include our floor chassis, our end wall, or cassette is another word for that. Our bathroom kit is an example. If you have bathroom pods, that's an object. Interfaces include our floor chassis or cassette to end wall. How is that connection being made? How is that connection being made in your factory? Do you have lift assist? Are you using screws? Simple things like that need to be figured out so that you can implement those things into your manufacturing documents. And wall-to-ceiling is another example of an interface in the factory environment. On the building scale, we have our volumetric module, of course, but we've got the other objects that exist in a building that maybe you're not manufacturing, but your module relates to. An example is the podium. In our 2 to 5 story affordable housing MVP that we're talking about here today, that would be, how does the module sit on top of the podium? Is it on a curb? Is it on a sleeper? How tall is that curb? How do you connect piping through the podium? Those are interface relationships between two objects. And of course, interfaces might be relating to objects that are the same to each other. So in a stacked volumetric modular system, an interface example is a module-to-module connection. So how does a module connect vertically and horizontally? How do you maintain your fire rating? Those sorts of questions that I'm asking, by the way, are coming from our stakeholders, from those user stories. We meet with our stakeholders often to kind of drag these things out, but we also just empathize and write user stories. So an example for architecture might be maintaining your fire resistant rating between dwelling units. How does your mate wall do that? And that needs to be designed into the system. And that is something that's designed into the system at an interface level because it's two objects relating together to create that barrier. The whole purpose of this is to, in our configure to order system, is to allow interoperability of parts. We need all of our pieces of our platform architecture to relate together to create our building overall. Something that's really important about this in configure to order is something called base modularity. It's something that Lego does really well, so I'm going to use it as an example. So base modularity in this, it's the little dot. The dot is our base modularity in Lego. Every Lego piece is based off of this one block, or this one dot. I think that sometimes our base modularity in the built world, because we're really trying to fill up a site, is like 1/32 of an inch. Let's try to avoid that. So a good lesson would be like 100 millimeters or 4 inches. Can that be an acceptable base modularity? Maybe you can go bigger than that and go to like 3 feet or 915 millimeters. So that would be another example of base modularity. But then you're basing everything in your space off of that base modularity, but having that allows you to have interoperability of parts. You can kind of understand with certainty how big and how wide and how much you can stretch modules within base modularity. Interfaces are very important because that's how everything connects and relates. In a configure to order system, what we need to remember is that the relationships that we're setting are the most important parts of that system. Buildings are complex. There's a lot of parts inside of buildings. We have gravity piping at an angle in the floor. We have our fire ratings. We have our structural requirements. We have connections to our lateral systems. All of those get picked up in our interface relationships. The example I'm showing here is our kitchen kits and bathroom kits, which are just digital kits. We're not doing pods, for example, and you can collect things in the digital environment. That's not necessarily how you connect things in the real world. But these kitchen kits and bathroom kits have certainty in them because they've got their QTO and their own BOMs, and they have all their data built in. And within those kits, there's certain relationships that are already set. We're not moving the bathtub, we're not moving the sink, we're not moving the toilet, we're not moving the stove. We know what they are. So that means that we can build in that known data into our platform architecture early. The pink and the orange zones on this plan are showing where product design is saying, hey, this is where our chases are in our open joists or our plumbing trusses or floor trusses. So we know with certainty that this is where plumbing needs to travel in order to get to the riser. The riser is in the same location on every module so that you can have, I like to think about it as like unlocks or like achievement unlocked. When you have the riser in the same location all the time, suddenly that vertical interface is always happening no matter what your interior layout is. So the achievement unlocked of doing that is that you don't have to have a 2-bedroom on top of a studio. You don't have to have a studio stack. You can have different unit types stacked on top of each other because the riser is always in the same location. So normally we're trying to force that vertical relationship with consistency, but if we're creating or building that consistency into our interfaces, then you unlock kind of new and different kinds of things, which is kind of exciting. I highlight drain waste vent here because it is a very challenging aspect of any modular system, just getting that piping to wherever it needs to go. So it's something that I may bring up again. It's important. Going through the process of identifying our objects and interfaces then leads to a map of our system. Now we know all of the pieces and how all those pieces relate to each other, and we can start to develop this scorecard for development. In this particular example, we're identifying our floor and ceiling assemblies, our mate walls, etc., as our objects for the volume, and then our interfaces inside that volume as well. When I say floor assembly, that floor assembly includes drain waste vent, for example. It's not just the joists and the girders or the rims and the sheathing. It's more than the structure. It's the plumbing. It can be the finishes. It is everything that lives on that floor when it's in the factory environment to get connected to other components. So it's more than structure. It is a system. It's thinking about the fire rating, the plumbing, the electrical, the structural, etc. All of it together, developed. Which means that when you're thinking through those interfaces, you're thinking through the interfaces of all those things as well. If your ceiling panel is disconnected from your wall panel in assembly, and you bring it together and connect it for final assembly, what's that connection look like? Is it a quick connection? How fast does it connect? Are you achieving your takt time still? So those are the kinds of things to think through when you're integrating more parts of the building system into your product. This is an example scorecard on the building scale. Same things that we've already talked through. We have our volumetric module, and we have our other pieces that might connect to it. In our Tracy facility at Volumetric Building Studios, or Volumetric Building Companies, and studio is the particular department that I work for, which is the design studio. We do corridor panels separate from the volumetric modules. Some manufacturers do the volume, corridor volume. We do together in one very long module. We do volume, corridor panel separately, and then a volume separately. So those get attached on site, which means that those become on-site relationships that have to be connected. Other examples of your building interfaces, especially for tall buildings, might be your lateral system. So in the steel systems that we're working through, lateral is a really big part of that. We need to build in relationships for tall building movement. And if that movement isn't being accounted for in the module, then it's being accounted for outside the module, and those things have to connect. Now that we have the map of the building, we can start to take those objects and interfaces through our design thinking roadmap. This is a diagram from IDEO that is a very generic way of describing design thinking, which is where we're diverging to create choices. We're creating a lot of ideas, we're putting them out there, and then we have to converge to make those choices. We have to select the ones that are winning in some way. This is my favorite diagram in the presentation. I feel this weekly. It's talking through the process of design thinking or product design, which is what we start with hope. We're starting with creating those choices. We have so many ideas. We're really high with our blue sky, like thinking. Things are good, things are exciting. And then we start prototyping and doing our cost analyses, and we're getting insight. And it's like, oh, okay, hopefully some of these ideas make it through. But then you get back over that line to happiness land and get your confidence because you know that you've done your due diligence and you have certainty now in the products that you're developing. It's a roller coaster. These are the steps in design thinking. They're not linear. They can go back and forth. You can start with define, then go to empathize, which is what we're doing here with defining the system. I'm going to walk through each of these steps. Empathize is what we talked through. We're all stakeholders in the process. We're at least end users. We're all familiar with housing. So we're stakeholders in the process, and we're developing user stories to understand what our stakeholders are looking for throughout the entire value chain. So our contractors, our users, our developers, our architects and engineers, and our shop drawing folks. So the people putting together the shop drawings that feed manufacturing. Empathizing with that gives us a baseline understanding of not missing something when we first start out. We want to have all that information up front so that we're thinking through not just right now and like the design process, but also can what we designed actually be built? Defining then defines the needs of that product. So we went through the process of defining the basics, like these are the objects, these are the interfaces. Each object has requirements that maybe aren't from the stakeholders. A mate wall has a 1-hour rating and an STC requirement. A corridor wall has its own requirement too. This definition supplies those requirements to those objects and interfaces. Ideate's the fun part. Ideate is the happiness of that chart, exploring, creating ideas, and then we go into prototype. And that can be a digital prototype. It doesn't have to be a physical prototype, although physical prototypes are great because they build muscle memory. And you're really getting in there and learning how to build it and experiencing what it feels like to make the connection. But we do a ton of digital prototyping. I'm very inspired by the last talk and AR and VR. And I think that there's a lot in that can be used in figuring out connections, especially when we're, it's like, hey, does this 6-inch space work to make this connection in the ceiling? And you have to stand on a ladder and really experience it. That would be helpful before investing in the actual physical materials to build it. And sometimes it's easier because everyone's so busy to be able to do it digitally where we have a little bit more control. The last one is test. Test means to actually test it for your sound and fire and things like that. But it can also mean getting sign-off from your stakeholders. Did you hit the mark? Did you achieve the things that you wanted to achieve, or did you not? So it's about receiving feedback. These are image examples of each of those steps. Empathize moved over one, but it's literally just sticky notes. And because we're a global team, we do them on Miro, but you can do them on any Adobe platform or anything. Miro's pretty accessible. And then we've got our scorecard. We've got some hand sketches of a connection. We have our digital prototype of that connection and an example of a fire test document that went out. Doing prototyping also helps us with continuous improvement before that product even gets to manufacturing. Again, this is all happening before the project delivery stream. We are sandboxed over to the side, figuring stuff out so that the product team can get projects permitted and work on that stuff so that we can keep feeding the factory. This last step is one that's added. It's not in the IDEO design thinking process, and it's called implement. We can do all the work we can to prove that our products work and make sense and get sign-off, but they need to be implemented. This can be done using software tools, but ultimately the company or the group that you're working with that is adopting your product design needs to have such buy-in that it is actually entering the project delivery stream. And you have to be using the same tools and speaking the same language as that first handoff, which is typically to our architects and engineers, so that it actually gets implemented. So use the same software, for example. That's an easy way to do that. We're working in Revit, so we go from Revit to Revit. And that's a good way of doing that. You can utilize templates for implementation. You can utilize Revit warehouses, which we utilize. But these are, and here is an example, but these are ways to start getting that data documented so that it can be used by other parties. Implementation in the product platform. Okay. This is an example of a steel system. This is a map, a warehouse map of our system. It's showing every possible object and interface. It doesn't have to be a real building. In fact, it should not be a real building because nobody would design a building that is this small of a footprint. But it's showing your lateral system, it's showing where your elevators might be, and it has a zoned area with a higher level of detail, which does not have to be populated across the entire building because we're anticipating what our clashes are going to be already. And the point of having this very, very thought out product design process is to eliminate those clashes so they don't happen. If you have clashes in your product zones in a project, then something wasn't thought through during product design. This is an example up here of some plumbing coordination that's happening before we even have a project. So it's just thinking through how the steel volumetric module responds to known plumbing zones. We know the vent's on the top, we know the drain is at the bottom, and we know that it's sloping and wants to be closest to the bottom as possible of the floor assembly, and the vent can just simply be at the very top of the ceiling assembly. And that means that we've pre-understood those zones using the rules that we set forth at the very beginning of objects and interfaces to design things. This also allows for different teams to be working on different parts of the building system. If you define your zones, then suddenly you know what the no-fly zone is. We define no-fly zones all the time. Like there's going to be plumbing here. It's not designed yet, but we know it's going to be here. Don't build structure there, please, and thank you, especially for access requirements. Okay, so a really big and important stakeholder in the product design process is manufacturing. We're going to now take our wood timber affordable housing product that we've spent the last few slides thinking through with design thinking and whatnot, and we're going to understand that in the context of design for manufacturing and assembly. The first thing to remember is that manufacturing is one step in this overall process. And if we zoom out on the overall process, we need to remember that each station, in quotes, of a design process for a building has a flow rate embedded into it. Flow rate is a term used in manufacturing to say how many units of something are going through each station and the entire process. It's really thought of a lot in the manufacturing process, but if the thing feeding into that manufacturing process isn't matching the flow rate, then something's going to happen there. And it starts before production drawing development. It can start with design and third-party approvals. Volumetric Building Companies is vertically integrated, so we have our own design team in-house, and we anticipate that there's going to be some project attrition. Not every project we design makes it all the way to manufacturing. So in the calculation of our mod rate per day, we need to understand that some of those projects go away, put a factor on that, an attrition factor for projects. We then move into production drawing development. I'm just using an example of a flow rate of 6 modules a day. So in production drawing development, say we're hitting 6 modules a day. That is perfect if that is our goal, because now we feed that into manufacturing, and we're getting really close to just-in-time production drawing deployment into manufacturing. That's a really comfortable place to be. We don't want to be under. We definitely don't want to be under, because then your production drawing team is always feeling behind. They're always feeling burned out, and they feel like they don't have enough time to feed the factory the information that it needs. It's a little bit better if you're producing production drawings for 7 modules a day when you have a 6 module a day output need. But we also don't want to build up a huge backlog of production drawings, because part of that first step in manufacturing is to do our continuous improvement. It's for manufacturing to review our shop drawings, to give us feedback, especially in a configured to order or modified to order system, where you might have changes that they're not used to seeing. In modified to order, there may be new details that they are going to have questions about and have good feedback on. And if you build a backlog of your production drawings, now you have to fix thousands of sheets, potentially, based off of that feedback. So it's really beneficial to match your manufacturing flow as much as possible in production drawing development. Typically, transportation has a higher mod rate per day. because it's the fleet going back and forth, and it's kind of easy to throttle that up and down, depending. And maybe your final assembly on site has a rate of 8 mods per day or something like that. And so you know that your 6 mods a day isn't going to create a backlog of module storage. It is really hard typically to get just-in-time module delivery to a construction site. It's kind of like it's a glamorous idea, and it doesn't sound glamorous probably to people not in the industry, but it is because it means that you don't have to store modules somewhere. It would be very exciting to be able to do just-in-time delivery to the construction site, but there's delays in construction, and so sometimes that's just not achievable. Now let's focus on manufacturing. So I have a video here of the Tracy facility. I'm going to turn the volume off, though, so that I can narrate over it. In our Tracy factory, we have parallel manufacturing processes that then feed into our primary assembly line. We start the floors right side up, flip them once to turn them upside down so that we're ergonomically installing piping in the floor, and then we flip them right side up again in order for them to then get fed into our final assembly line. Parameters for this flipping ideally would be part of that design for manufacturing and assembly. Then we have our wall line. It's another parallel approach. A lot of this is automated for framing and for sheathing attachment, for first sheathing attachment. And we're even looking at moving some of that taping and mudding for the drywall off the final assembly line and putting it on our parallel assembly lines. The more work that you can put on your parallel assembly lines, the better for manufacturing. It's faster. It makes for a faster tack time for your final assembly line. The genius behind this manufacturing layout is our CTO, Helena. Helena is a fantastic speaker, and I hope everybody here gets a chance to hear her speak about this manufacturing design process, which is her world, less so mine. This is our final assembly line showing how the modules are becoming more and more complete as the stations move on, and you're seeing piping on top of the ceilings for domestic hot and cold water and fire sprinkler and some vents now too. Now I want to talk through how do you design for that. So we've got this panelized process, and this is the whole purpose of this Lego model, is to walk through that panelized process. And I realize that this mic is here, so I'm going to have to move it over. All right, so when we're designing for panels, panels are much easier to control for tolerance than volumes. So two-dimensional pieces, like this, which just broke. I promise it's not because of my craftsmanship. So two-dimensional elements like this are much easier to control for tolerance constraints. You can use jigs for this, and you can build it on a table, and it can be controlled very tightly. So it's much easier to do that in a two-dimensional component, so that's why it's separated like that in our Tracy facility. I also realize that this is a big room and this is a small model, so apologies. It's very basic, but you can definitely come look at it later if you want to. All right, so we start with our floor. And just like in the overall process, we're working on things with flow rate. So if our goal is 6 mods per day, we know we need 6 floors. That's basic math. That's easy. So we've got floors. Then the next step in this particular process is to bring in your mate walls. In your factory environment, and how you would design this with your thoughts around manufacturing is if you have lift assist, for example, or do you not have lift assist? How are you moving this huge mate wall to your floor? And is it approaching it from the top, or are you having to tilt it up? Those are 2 different movements, and those movements impact your interface. Your interface design has to relate to that movement. If you're going from up to down, you can use things like pins, or if you have an exposed wall on the inside, you can just screw it down. If you're having to tilt it, maybe you have an angle stop on one side, so when you tilt the wall up, you're able to stop it against that angle, and you know exactly where it needs to be. It's like a built-in floor jig or guide. So that movement in your factory is important for developing those interfaces. and it's important to know. So manufacturing becomes a very close friend when you're developing that interface. Next is with corridor walls and end walls. Similarly, those are coming in and dropping down potentially, but that means is that now your end walls can't have a piece sticking out of it, because now that piece is in the way. So that's another aspect of movement in the factory that impacts how you design connections. And then lastly, the ceiling also wants to ideally drop down. If you don't have lift assist in your factory, then these pieces are too big. Your pieces or your objects in your system would be smaller to account for that. And then, of course, the ceiling coming down. And then, again, with your end walls being balloon framed in this example, a Lego balloon framed, you can't have something sticking out of that end wall because it'll interfere with how the ceiling is setting against it. Lastly, construction is final assembly. How do you account for final assembly? A very important thing in any manufacturing environment are tapered or flared edges. When we design those tapered or flared edges, especially like in the cone shape of this pin, this is a set pin. Imagine it being like a one Lego dot, and that's how your module finds its placement. The fact that it's smaller on the top means that it has a better chance of actually getting to the receiver, and since it's flared as the module lowers, it's finding its location, its proper location, refining tolerances. So that flared edge allows you to build in tolerance control without the use of surveying equipment. You're doing it with the cleverness of your connection, and that's it. Another aspect of final assembly is making those MEP connections on site. An example is bringing those connections outside the finished unit so we don't need work done inside the finished unit, and then making it ideally nice enough that all of our stakeholders approves this approach, because it is a bit of a different approach. But it does give the corridor a bit more articulation, and it brings all of those connections outside the unit to allow for easier access. And now I think I'm done. Thank you, everybody.
All right, so opening up for questions for Sara. Sara, thank you so much for this amazing presentation. It was like a full class on how to how to design for a productized building, and I'm very impressed. So I'm going to kick off with a question for you. You kept me like thinking about the case of the hospital, right? So. In the hospital, I remember the early days, we were like, oh, let's modularize everything, let's ship on trucks, everything. And then I love the chart that you put with the curve, right? So many ideas, and then you start understanding the constraints, and then you come to reality, right? And I love that. So we ended up, at a certain point, we ended up developing a matrix that's very similar to yours. Like, what's the engineering to order components, what are the configuration to order, and what's the standard components within one project. So we could clarify to everybody and build agreement and what does it make sense to really, industrialize versus... anyway, so, and that was part of a reflection of all these constraints, like truck sizes and loads and weights and policies and customer involvement and the level of customization. So anyway, there are a lot of constraints. So my question to you is, what kind of challenges did you find for the FMA? And especially, I know you guys have operations in different locations, different cities. Yeah. And I'm curious to understand, like, building codes or constraints that you have found for the FMA.
Yeah, thank you for that. So it is completely possible and good to have a sort of like a product platform for a project, which is what you're describing for the hospital project, right? So you're starting with developing that system for that particular project, and you're building it up. And I think that that's fantastic. I think that the way that we're approaching it, and the reason that I'm sandboxed with my team to develop product, is in order to make those products accessible to more projects, and thus creating a more consistent environment for a manufacturing team. There is a challenge with the global team, as you mentioned, especially because we are, it's not necessarily the global team, it's the global market. So with the global market, we're trying to reach into so many different places in the world with very different building codes. One of the first things we did when understanding this is develop a table of different building codes and their requirements. So we have different building codes like IBC, Type 1, Type 2, just in case we want to look at that one too. This is for steel construction. And then looking at what the requirements are in Canada, looking at what the requirements are in Europe, and even on different coasts of the US, because we're very fun and exciting in the US. We have different codes across our country. So a way to just document it, and so it's apples to apples comparisons of different rating requirements. That's one way to navigate understanding that code requirement. And then for DFMA, I think that the challenge is the difference in testing requirements and the systems as well. But the biggest challenge isn't actually with code, it's with supply chain. Different materials are accessible from different areas. So even though we're trying to create a platform that's consistent between locations, we may find that the material that we're specifying for the floor sheathing isn't actually available. So we'd be shipping something from the US to Poland back to the US on the product. So we don't want to ship that many times because it's not very friendly for the environment, and also it's a lot of money.
That's very good. So a related question, how do you work with the building department to get approval of these units if they have not seen it before?
In California, we work with the state. The state reviews and approves the modular drawings. And there are, essentially, it's like design documentation for just the modules themselves that is in the project. And typically there's an MAOR set, a modular architect of record set, and a design or site architect of record set. The modular architect of record set goes to the state for review and approval, and they'll check it for all the things that they check it for, accessibility, fire and life safety, structural requirements. And it's actually typically a third-party reviewer that does it, that the state has indicated as an authority to have the ability to do that. Right now it's typically from project to project, but there is the possibility of having like pre-approval on units from the state agencies, and then you just submit how those units are adopted in a project in the future. But it's mostly the former.
Thank you. A lot of related questions here about the challenges. The next one I have is from Zig Rubel, also from CFI, and he's asking, can you talk a little bit about the transportation of the final product and the impact on the product design?
Mm-hmm. Transportation and site logistics is typically part of our pre-construction user story setting. So it's thought through early on. And we also have our design metrics for size that follow, in California specifically, CHP guidelines for shipping large things. So we follow those guidelines, and that's, of course, a huge impact on the product design because we, from the first pass, from the very beginning, we have limits on the size of the module, shipping size requirements, oversized load requirements. So that's one thing. The other thing that you're probably thinking about in that question is the fact that when a module is going down the road, it's vibrating, and it's moving around, and it's bouncing, and it's turning around corners. What is done to maintain that you don't have cracks and that the product is stable during that? So there are temporary blocking and things like that that are installed to maintain module stiffness, and so that's one way to do that. One thing that I forgot to mention in the presentation is that when we're thinking through product design, an aspect of it is the idea of time, especially in industrialized construction. So the process of, when I say time, it's like what is the journey of this product to its final location? And we call it like conveyance. So from in the factory conveyance to final assembly conveyance, what adaptations to the product need to happen in order for it to be conveyed properly. And so there's different ways to allow for pick points, things that don't necessarily matter in the final building assembly, but matter on the module's journey to get there.
Very good. So I guess, again, I have a lot of questions. You guys have a lot of opportunity to talk to Sara.
I ended a little bit early, too, so now we get more questions.
Yeah. So I have one more here from Larry Hillman, Coversight. I'm sorry, Larry. Converted, thank you. Larry is here, right? Yeah. So how do you incorporate life cycle costs, management, and maintenance into the model? Do you or could you model usage, wear and tear, and maintenance into the model?
Yeah, fantastic question. I think that there is a few different prongs to this one. What I didn't talk about during prototyping is the number of tests that we put on the product. So there's a lot of analyses. There's a cost analysis, so there's the cost analysis of the product itself. There is energy analysis on the things that we're putting into it that can be done, and that we're certainly doing, especially for our zero carbon initiative. For that particular aspect of things, we need to know if the design is following through with our energy objectives up front. And that would be an energy analysis like would be done for a Title 24 analysis. And then we have a sustainability manager, part of Helena's team, part of Platform, that would also do an analysis on our products to make sure it's hitting our company's sustainability goals. So those are sort of the upfront processes that we integrate into product design. After a product is released into the world and we want to understand data for that, we would use conventional metrics for that as well. So post-occupancy evaluations. We don't have sensors currently built into our modules to actually measure energy use, but that would be something that we're open to including in the future with potential technology partners.
I have here a related question from stakeholder standpoint of view, right? How do you actually incorporate the stakeholder input into product development?
Yeah. Because we're vertically integrated, I have access to a lot of our stakeholders in our company. And so during ideation and during sign-off process, we actually meet with all of them, usually in a big meeting, but we can meet in groups as well. And they're part of the design process. So it's kind of very similar to community engagement that we just heard about, but it's with your internal partners. And that would be especially during ideation. And so it's a moderated ideation environment where everybody comes together and generates ideas, and then especially at sign-off when they're giving feedback on if we missed the mark or if we succeeded in actually getting what they wanted. And so it's actual meetings, and we document the information in our product development roadmap document. So it's all documented so that we can reference it, especially because of short-term memory sometimes. We want to make sure that everybody remembers what we committed to early on.
Well, that's very good. I'm also curious. I visited a pod factory, and I was very impressed that they said it took them 5 years to actually create a pod that would be perfect in terms of buildability. So can you tell us a little bit, how do you engage people within your company to give feedback and improve on the next evolution of your product line?
Yeah, sometimes it can be challenging because everyone's so busy. So I'm competing with projects in the product delivery stream or project delivery stream that are about to hit the factory floor. So that can be a bit challenging, but it's really just about committing to setting time on a calendar and approaching them. We are a global company, so sometimes it can be hard to approach somebody in Philadelphia when I'm in California. So we utilize digital tools for that. We're on Microsoft, so Teams is always open, and I'm constantly chatting and trying to get feedback. We have our meetings over Teams, which also utilize or can benefit that. But I think that Typically, the best way to get feedback is by actually building the mock-up, because then you'll get unsolicited feedback as well, because it'll be out in the wild and people will be able to see it and understand it, and then you'll get feedback. Another part is when we do enter the project delivery stream. So this is an important way of getting feedback as well, and very necessary. When the shop drawings are developed and they're about to be released to manufacturing for review, we set up a review period for that to happen. And this is why we don't want backlog of drawings too, right? So we want to get feedback on a set of drawings that then feeds into the next set of drawings for that project. And so that's part of our continuous improvement process and feedback cycle, especially with manufacturing, is for them to provide comments on the shops. And those shops are connected to our products. So we're learning through deployment in projects what some issues might be that then can get fed into our project or product platform.
That's very, very good. I have a question from Larissa Alarcon. She's there. How do you build size flexibility in a prototype?
Size flexibility?
Yes. Yeah.
In a prototype? Prototype's one of those words where we all have a different definition of what prototype means. When I think of prototype, it's actually a physical thing that we build. So I'm going to talk about how we build flexibility into our configurable units. So if we remember the rules of the CTO system and interface rules, the most important thing is to not break down relationships. So flexibility is allowed where that relationship doesn't exist. And what that means is if your plumbing zone is the first 13 to 20 feet of your module, probably more like 10 to 15 feet of your module, then after that, you are free to grow the module as much as you want, because it's not impacting any of your predefined relationships that are really important to the success of your product system. Same with width. If it's outside of the area of that relationship, then you're free to change width. And so it really depends on the particular rules defined in the product system that we're talking about. And so in configure to order, that would be the rule. In modify to order, it's almost like you're free to stretch it as much as you want, wherever you want, because you know you're modifying all those relationships anyway.
That's very good. And then the last one I have here is very similar to the challenges we were talking about. It's really, we understand you have a lot of work in California, and is it more challenging with the seismic requirements? And this question is coming from Sarah Noy from UCB Capital Projects.
The seismic requirements really impact the lateral system in the building. In the steel system that we're developing, for example, we understand the need for wind loads and seismic loads, and so that's built into the prerequisites of the system. So I don't think that it's more challenging as long as it's known early on, and you need to define it in those objectives at the very beginning. So if a market objective for product development is a seismic zone, like California in the Bay Area, then you know from day one that you're committing to lateral forces. And then that gets built into your objects and interfaces down the road. So I don't think that it's more or less challenging. It's just that it needs to be defined early enough to make it into the system.
That's perfect. So Sarah, like I mentioned, she's going to be available. You guys can reach out to her if you have more questions. I really want to thank you. For me, your presentation had, lean design concepts, lean production concepts, modularization, industrialized construction. It was it had gold nuggets for everybody that's here, either working on a manufacturing or verticalized company or working on a project environment. I think there are so many key takeaways from your presentation. And I really appreciate you taking the time and presenting to us. Thank you.
Thank you so much. Thank you, everybody.